Good morning, good afternoon, good evening, whatever time of day you are deciding to watch lecture 19 videos. Hi, I hope you had a wonderful weekend and were able to do something good for the old mental health-aroo. Just before we get started, I have a couple of announcements. Big thing is that you have your second exam that is available on Canvas and on Connect. It is due on Sunday at 11:59, and it will hard stop you at 11:59. So be sure that you set aside the time to do that. It's the same exact format as your first exam. So you'll have a combination of multiple choice, true, false, fill in the blank, and then finish off with some short answer questions. So be sure to give yourself time for that. And, big thing with the short answer questions, please don't fully rely on Google in order to give you those answers. The likelihood that Google will not give you the right answers or the answers necessarily that I'm looking for is quite high. And I have told us throughout this whole unit which questions I would ask as a short answer question. So hopefully you've been able to make little notes for yourself. And I will also post a self-paced Kahoot if you want to do that for studying, if you would like. And also the first exam covers chapters 4, 5, 6, and 16. So, we talked about chemistry of water and chemistry of seawater. And then we jumped into the atmosphere and then rounded it off with climate change. So please be sure to get all up and prepared for that. It's open book, open note, open resource, all of the things as usual. So hopefully that will be all okay. So just reach out if anything is amiss. And if there's any technology problems that come up, please reach out to me immediately. I am technically on spring break for SF State, but we're not on spring break yet, so I'm around, so feel free to reach out. Speaking of, next big announcement is that it's spring break next week. Woo, woo, woo! So there will be no assignments, no extra videos, no homework or anything like that. So yay, break time. So that will be good. And hopefully I'll be able to get all caught up with grading stuff and things of that nature. So huzzah! The break is finally here. Almost here. Okay, so all of those things out of the way. Oh, sorry, one more thing. Your final draft for your personal letter is due this Sunday as well. So please make sure that we get that turned in so I can start chipping away at grading those. Okay. Again, please reach out if you have any questions. A big thing that I would suggest in terms of writing is to write a whole bunch and then put it aside for a day and then come back to it and read it out loud. It really slows your brain down to catch little minor mistakes that may be there. I catch my mistakes all the time doing that method. That's not just for writing here, that's writing anywhere. So just some tips if you so choose to utilize them. Okay, so we're moving on. We're going to continue forward, and we have finally gotten to the part of this class where we start talking about the oceans. Holy bananas, I know. I told you it'll take half the semester to get there, and here we finally are. So, huzzah. So starting to talk about the oceans, we need to bring up some keywords. I know there's a lot going on this page, so take your time, maybe even give the video a quick pause if needed. But these are some major keywords that we're going to be talking about throughout the rest of the semester, basically. So when we talk about something called the mixed layer, that's where this surface layer begins, right at the very, very surface, what our eyes see when we look out at the water, anywhere from tens to a few hundred meters thick. and how thick that surface water is, or how thick the mixed layer is, will vary from ocean to ocean. And we'll talk about why there's variation all around. The next term here is the thermocline. So the thermocline extends from the bottom of that mixed layer to about 1,000 meters down, which, remember, 1,000 meters is about 1 kilometer. And it's this region of really, really sharp temperature change. So basically, like, you can think of it this way, like if you have a water bottle next to you or something, and you touch your water bottle, it's probably cool to the touch. So the difference between the temperature of your hand and your water bottle is really intense, right? Whereas if you were to put your hands together, even put your hands on your arms, there's not a huge temperature change because you're all like one body, right? Or if you're like me and just have constantly frozen hands, then maybe there is a temperature change. But internally, there's not a huge temperature change, right? A silly analogy, but it works. Next, we have the halocline. So the halocline is a region of sharp change in salinity. And then the pycnocline is a region of sharp change in density. So maybe you're kind of picking up on a pattern here where cline means sharp change. And then the term that's before that is indicating the variable that we're talking about. So thermocline, thermo is temperature. Halo is salinity, and pycno would be density. So sharp changes in these variables. And then on the flip side, we have some terms that tell us things about being the same. So all being the same. So isothermal is a layer of water that's the same temperature. The isohaline is a water that has the same salinity. And isopycnal is a layer of water that has the same density. And it turns out, actually, and we'll see this in a couple of the slides today, that a lot of the ocean beneath a certain layer is isothermal. It has the same salinity. It has a big isohaline is isopycnal. So it's like a lot of the ocean is very, very homogeneous, meaning it's all the same. And we have to remember that we're now going to be talking about the ocean in this 3-dimensional space. It's no longer just what we see at the surface. We have to consider the whole kit and caboodle of the oceans. Next 2 terms here, perhaps we've heard of one of them before when we talked about ENSO, or the El Nino Southern Oscillation. Big thing here is upwelling. So this is upward vertical motion of water, and this process provides nutrients from the deep ocean waters up to the surface. Whereas downwelling, this is downward vertical motion of water, and this provides oxygen to the deep ocean waters. So upwelling, just a kind of little tidbit of info here. Upwelling is super, super important for our coastline here in California. Basically, and we'll learn a little bit later, but basically winds move water. And there's this whole process of winds coming from the north, going down the coast to California. And overall, this actually transports a lot of water out into the middle of the ocean, out into the middle of the Pacific Ocean. And that water has to be replaced by something. It's conservation of mass, right? So we have to just do the thing. We have to replace the water, right? So think about it. So if you have like a tub of water and you slap your hand down into it, we're not playing Moses and we're not parting the Red Sea, right? The water has to return back to where it initially was, or like it fills in the space that you tried to negate. And similar sort of idea here with upwelling and downwelling. All right, so now we're going to look at a couple of these ideas a little bit deeper, starting with temperature. So this is a very simplified version of what temperature does as you go down the water column. Temperature is on our upper x-axis, depth is on our y-axis here, with the surface being up at the top. Notice some of our other key words that we talked about. So the mixed layer is here, the thermocline is here. See how there's this really sharp change in temperature in this yellow area, in this thermocline? That's exactly what we would see. And do you think that this pattern would be the same all over the world? Think about it, think about it, think about it. Think about, sun angle, think about seasonal variability, think about oceanic temperature at the surface. And if you guessed that that this is not the same pattern all over the world, you would be correct. Huzzah. So what we're looking at here is temperature in the middle latitudes is on the left, which is where we're located. The low latitudes, meaning the tropical regions, and then the high latitudes over here on the right. So the big thing to really keep in mind here is that lower latitudes have a very permanent thermocline. So they're really, really warm at the surface. And there's this sharp, sharp, sharp change in temperature until about 1,000 meters. And what we can notice is that like a lot of the temperatures here really are getting down to near 0 degrees, but not quite. And then the middle latitudes has a seasonal thermocline. So in the summertime, the waters can get much warmer, but in the wintertime, they'll cool down. And then the high latitudes are pretty much cold all of the time. There's not this variation in temperature here. And we'll learn later on in the semester that this is actually really, really huge in terms of productivity. So how much life happens in a space. So when you have a permanent thermocline like this, you're actually impeding on any sort of mixing from the deeper oceans to the surface oceans. And so the surface oceans tend to be nutrient poor. So like the open, warm tropical oceans are actually not very productive, which is really kind of fascinating. Having a deeper look at the middle latitudes area, this is all these different lines here indicate a different month, and like which month has the strongest thermocline tends to be about the end of summer in the northern hemisphere, and the not as permanent thermocline or not as persistent thermocline kind of in like the springtime areas or springtime times. And just to finish up with temperature, looking at the distribution of ocean temperatures, this is a histogram of ocean temperatures in cubic kilometers, meaning that about 75% of the ocean has a temperature between 0 and 4 degrees Celsius. So a lot of the ocean is really cold, basically. And since deep sea water originates in the polar regions where cold, dense surface water sinks and flows towards the equator along the ocean floor. So all this super cold water starts actually up in the Arctic, which I think is really quite fascinating. And then if we were to look at ocean temperatures, this is looking at 150 west. So if we remember our latitude and longitude, this is actually slicing through the Pacific Ocean. And what we would see, it's like a bathymetry chart here. I do not know what the deal with 50 degrees north is. It's not land, but the black stuff is land for sure. This is Hawaii. But what we can see here is the surface waters tend to be warmer than the deeper waters, and also the colder waters in the polar regions. So the 60 degrees south is over here on the left, 55 degrees north is over here on the right. So this is just looks like a whole lot of blue, meaning that a lot of the ocean is quite chilly. So that finishes up temperature. So in the next subsequent videos, we'll look at salinity and density and dive into some circulations that we see around the oceans. So thank you very much for your time and attention, and I'll see you on the flippy floppy.